Hello guys, welcome back to the channel. Today we are doing Leetcode 1123 LCA, lowest common ancestor of deepest leaves, and this also happens to be the POTD for today. So the problem statement says given the root of a binary tree, return the LCA of its deepest leaves. First of all, we need to have this understanding, what do we mean by lowest common ancestor? What does this phrase mean? Right. Recall that the node of a binary tree is a leaf if it has no children. The depth of the root is 0 and the depth of the nodes which follow is d plus 1. So for example, the depth of the root is 0, the depth of these two nodes is 1, of these two is 2, and then of these two is 3. Right. So the lowest common ancestor of a set S of nodes is the node A with the largest depth, such that every node in S is in the subtree with root A. So again, a very difficult set of English, but then it's very simple. For example, देखो, what do you need to know? Lowest common ancestor of deepest leaves. Let's remove this word for now. Leaves. What are the leaves over here? This is a leaf, this is a leaf, this is a leaf, and these two are leaves, isn't it? But then when we introduce the word deepest, what does that mean? It basically distinguishes these two leaves from the other ones. Makes sense? Why? Because they are at a depth which is +1 as compared to the other node's depth. And then it could have been like this as well. For example, if I had, for example, two nodes of 7, then these two nodes would have been the most deepest leaves, right? Then I would have to ignore this, this, and this. Even though that they are leaves, I would still have to ignore them, right? So what we have to do is, first things first, we have to figure this thing out, that which leaves are the deepest, right? That's the first thing which we are going to do. If you think about it, we are building our approach now. So the first thing which we are going to do is we are going to try to figure out what are the deepest leaves. Okay, a high level overview. This is just sort of like a bird's eye view of how we are going to solve this problem. Now, once, let's say we have figured this out, that 7 and 4 are the deepest leaves. Now what I need to do is find the lowest common ancestor. What is ancestor? Ancestor is like, who's the parent of this 7, who's the parent of this 4. So 2 is basically the ancestor of this, right? Root is basically the ancestor of this entire tree. And for example, if I say, if I talk about the left subtree of 3, then 5 is the ancestor of the left subtree, because you would see that 5 is the parent of this particular tree, isn't it? All of this tree is being sort of derived from 5, and 5 itself is being derived from 3. Similarly, this one is the ancestor of 0 and 8. So once we have figured this out, that 7 and 4 are the deepest leaves, now what do I need to do? I need to figure out the lowest common ancestor. So which ancestor is the closest to both of these and also common? Obviously, since I'm talking about two different nodes, I want to see which ancestor is the closest to both of these nodes, right? And also common. So you can say common closest ancestor or lowest common ancestor. Both of those things mean the same thing. It's important that you understand basically the philosophy and the concept, right? Okay. The very simplest approach, which I mean everyone could think of this, is that somehow along with these nodes, you also keep track of what? Just think about this, of their parents, of each node's parents, right? Now what good is it going to provide to me? If I know that 7 has a parent of 2 and 4 also has a parent of 2, okay, what I'm going to do is I'm going to see, okay, these two are the deepest nodes, Let's have a look at their parent. Okay, let's have a look at their parent. Now, since the parent is the same, obviously means that this is the lowest common ancestor which I'm looking for. So I'll just return this as my answer. But then this problem is obviously not as simple as that. There could be multiple scenarios. You see, if we take a look at the other examples, then I have this sort of a situation, root. So it's whenever you have a single node, it is the LCA of itself. This is a very important statement which is written over here. Similarly, you have a tree such that 0, 1, 3, and then you have null over here and then 2 over here. So again, this is the deepest leaf and the LCA of it is going to be itself because it's a single node. Whenever you have any single node, for example, in a scenario like in a scenario like this, whenever you have a single node, the LCA of it is going to be itself. So you will have to return this particular node as the answer. It is itself going to be its LCA. Okay. The other scenario, the second scenario could be that you have these two nodes as the deepest leaves. So in this scenario, obviously you're, answer me on this, that this is the closest common ancestor of both of these nodes, right? The third scenario is when our deepest leaves, both of them belong to different subtrees. So you see, the parent of this node is this node, the parent of this node is this node. For example, let's say that this is 1, this is 2, this is 3, this is 4, and this is 5. So 4's parent is 2 and 5 parents is 3. When I compare both of these, I do not get the LCA. Why? Because they are not the same. So what do I need to do? Then basically I travel upwards to 2 and 3. And then I see who is the parent of 2 and who is the parent of 3. At this point, I get my answer. As soon as I get the same parent, that is my LCA. And you know what? This could be very different as well. For example, just think of this particular scenario. Let's say you have 3 nodes, or maybe, for example, let's say you have more than 3 nodes. Let's say you have this sort of a scenario. Okay, so these are all the deepest nodes, right? So what you are going to do is you're going to track the parent, or you can say you're going to track the ancestry in this question. That's actually the beauty of this question. First of all, you recognize what the deepest leaves are, and then you track their ancestry. So you know the leaf of the parent of both of these nodes is this particular node. The parent of both of these nodes is this particular node. The parent of this node is this node. So now at this point I do not have a lowest common ancestor. Lowest common ancestor is always one single node, isn't it? These are 3 different nodes. So what I'll do is I'll see who their parents are. This node is its parent and this node is the parent of both of these. And who is the parent of both of these nodes? The root itself. So the answer of this sort of a subtree, of this sort of a problem, is going to be the root itself, right? I hope the question is clear. So up and until this point, what have we discussed? We have discussed all the 3 major cases, and we have discussed how we are going to build our ultimate approach. What we are going to do is 2 things. We are going to keep track of parents. So who's the parent of 7, who's the parent of 4? 4 is 2. For example, let's say I had a node over here as well as 10, right? Then 2 wouldn't have been the lowest common ancestor. Let's see what would have been the lowest common ancestor. The parent of this is 8. Now I have I have 2 different parents, right? So what I'll do is I'll go to the parents, this, and I'll see what their parent is. 5 and 1, still not the same parent, right? So I'll go to the parents. I'll ask them who their parent is. 3, and I'll go to 1. I'll ask who its parent is. 3. Now I get the same parent. So 3 is basically the LCA. And what I want you to do is actually, pause this video at this moment and try to code the solution up by your own. All right. But again, it's not saying that we won't be coding it up. we are obviously going to look at what the solution is. So the solution which I'm going to try to explain to you is a bit more intuitive, and it's a bit more you can say logical sort of a solution. So in this video we are going to look at this particular solution which consists of like more than 100 lines, but then it's very important, it, you know, there is proper separation of concerns, and one function is only doing one job and all of that. So you're going to have very a greater ease of understanding what we are doing over here. In the next video, what I'm going to do is I'm going to show you how the recursive approach looks like. So we're going to, you know, we are going to have both of those approaches, and then we can very easily grasp the fundamental concept when we compare both of these. Again, the thing which we are trying to do is the same in both the concepts, just the implementation is a bit different. Okay, right. So as you can see over here, I have taken two different maps. First of all, I have taken a child to parent map, so that what I can do is, you know, I can keep a track of which node has what parent, and then I have another map which is node level, so that I can keep a track of which node is present at which level. Makes sense? Because that is very important as well, right? I need to figure out who those nodes are, which are those nodes which are present at the very last level. So this is present at level 0, 1, 2 and 3. So I'm keeping track of two things. One is the parent, which is 2, and the other thing is the level, and I'm doing this in the form of a map for every node. Okay, so the parent of this is 5 and the level is 2. Similarly, the parent of this is 3 and the level is 1. The parent of the root is going to be null, obviously, and the level is going to be 0. Okay, so I have these two maps. The first thing which I do is I calculate what are the maximum number of levels that I have. So in this scenario, the maximum number of levels that I have are 3. So let's have a look at what this BFS function does. Okay, what this BFS function does is something like this. It's what is it going to receive? First thing, it's going to receive the root of the tree. It's going to receive the child to parent map, which is right now empty. We are going to populate it. Okay, and it also receives the node level map, which is right now empty, and this function basically populates both of them. Okay, so how does it do it? How does it do it? Let's have a look. So we can also even, you know, dry run this. I make a queue, and that queue is initially obviously empty. What I do is I push the root inside of it. So I push 3 inside of it, and just keep in mind that I'm pushing the tree node. I'm not pushing the integer value, I'm pushing the tree node. Okay, then what I'm going to do is against the map that I have of this particular map, child to parent map. Okay, right now I've taken a very simple name over here, but then this is the child to parent map. So what I'm going to do is I'm going to say the root 3 has no parent. Okay, the root 3 has no parent, right? All right, the level is currently 0. How many nodes do I have in the queue? I have just one node, so I'll be processing just one node. By the way, this is, if you don't know what this is very simple, clean breadth first traversal. But then what I'm doing is I'm in one iteration, like of the outer loop, I have two inner loops over here. All right, in the inner loop, the inner loop basically processes all the nodes in one level at one time. All right, so you can say that the outer loop is going to run once for each level, right? So I just have one node over here. I'm going to process one node. What I'm going to do is I'm going to save this node in front. Okay, and I'm going to remove it from the queue. Then what I'm going to do is I'm going to assign it the correct level. So I'm going to assign it a level of 0, because level equals 0. So I'm going to say that at the place of 3, please assign it a value of 0, because 3 exists at level 0. Okay, all right. Then if front dot right exists, please push it in the queue. And if push it in the queue, and also keep track of who the parent is. Okay, MP of front right, which means that the parent of 5. Who is front dot right? Front dot right is 5. So parent of 5 is front. Who is front? resultant is 3. So parent of 5 is 3. And similarly, I do for front dot left. So what is front? If does front dot left exist? Yes, it does. So what I'll do is I'll push it into the queue, and I'll say that the MP of front dot left, which means uh, at the place of 1, please insert 3 because the parent of 1 is 3. And I'll, after I have processed, after this while loop ends, what's going to happen is I just have one node, right? Initially, I just had one node in the first level. So it's not going to keep on continuing. It's going to just increment the level. So my level, which was initially 0, now it's going to become 1. Okay. And I have removed this particular node from my tree. So again, I'll push the nodes for 5, I'll push the nodes for 2, so on and so forth. So each node, ultimately, what you're going to have an idea is each node is going to know its parent and it's going to know its level. Each node is going to know its parent and it's going to know its level. Okay. And as soon as we find out the common parent, we return it as the LCA. How we are going to do that is going to come up later. Okay. All right. And ultimately, what I'm doing from this function is I'm returning the number of levels. Why I'm returning level -1 and not level is something which I leave up to you to figure out. Why am I not returning level and why I'm returning level -1? Okay, I'll put this the link of this particular code in the description section. All right. Having said that, what do we know? We know that this particular BFS function, it populated the child to parent mapping, and it also populated the node to level mapping. So which node is present at which level, right? This BFS function. And one thing which is also did, it told me the maximum number of levels that I have inside of whatever tree I'm working with, right? Then what's the second thing which we need to do? The second thing which we need to do obviously is keep track of, after finding out the lowest common and after finding out the parent of each node and the level of each node, I need to figure out what the deepest nodes are. 7 and 4 are the deepest nodes. So for this particular, by the way, I could have done it in the same function, but I chose deliberately to do it in another function so that it's a bit easier for us to understand. Okay, so max level I have, now I'm trying to figure out what the deepest leaves are. So for that particular purpose, I have another function. Again, the very same thing with just a very brief difference, and that is that if the node, it's the same breadth first search travel, so literally the same. The only addition is that I have made a vector of tree node over here. What I'm doing is, in the node level map, I am checking that the node which I am currently processing, is it present at the maximum level or not? Maximum level is something which I passed over here, which I calculated over here and I passed over here. I'm just checking if the node which I'm currently processing in the queue, is it associated with the deepest level that I have? If it is, I will push it in the queue, in the vector which I have made over here. Okay. And so thereby what's going to happen is, you can very clearly understand that these two nodes 7 and 4 are going to be in the leaves array, and I'm going to return the leaves array from here. Okay, and obviously since I return it, I'm going to capture it over here. So is that clear? So at this point, we know what the leaf nodes are, we know the child to parent mapping, and we know the node to level mapping as well. Not that we need it right now, but then we know everything that we need to know. Now the question becomes very simple, right? You just have to do a couple of if conditions. So you see, if you have just one node inside of leaves, let's say, just forget about this 4. Okay, let's say you just had this 7. Then what did I say? The question said that if you have just one deepest leaf, then it is going to be the LCA of itself. So that's what I'm doing over here. If leaves dot size equal 1, just return the only single leaf that you have as the answer, because it's going to be the LCA of itself. Otherwise, what do you need to do? Just like we did at the very start of the question, you need to compare the parents, and that is exactly what we are doing. We are not doing it recursively, we are actually doing it iteratively, but you could very well do it recursively as well. what we are doing is I have made a parent vector over here in order to keep track of the parent of each leaf and then see that if it's the same or not. Okay, so what's going to happen? What's going to happen is, first of all, I have over here a while loop. The first thing which I do is I populate the parent array. I say that inside of parent of I, which means over here, please see who is the node of this particular leaf. You see, leaves of I. What is leaves of I? Leaves of I is nothing but an array which has these two nodes inside of it, 7 and 4. So what do? I say that please make this a key, and inside of our map, check who the parent of 7 is. Whoever the parent of 7 is, please assign it in the array parent of I, because you see this is index number 0, this is index number 1. Alright, so parent of I becomes 2, and then for this particular thing, parent of I again becomes 2. Then what I do is I calculate the overall parent, and you could do this thing with multiple approaches as well, right? You could we will talk about it after we discuss this approach. We will talk about the multiple approaches afterwards. I say that let's assume that the overall parent is 2. Okay, we are assuming this, that the overall parent is 2. Okay, if I take a boolean variable over here which I assume it to be true, then I compare from index number 1. I start comparing from index number 1, and I say that if parent of I equal overall parent, all good, nothing to do, continue. Okay, because the parent is, this is the overall parent, right? OP, and this is also the same, so no worries, just continue. And then since we just have only 2 nodes, this for loop is going to break. If all parents same equal true, return overall parent, which is 2. In this scenario, it becomes true. But what if, देखो, what if I had 3 leaves? What if I had this leaf as well? Then scenario would have been a lot different. And you know what? Let's change this scenario a bit. Let's not let's make it even simple. Okay, let's remove these two conditions, and let's say that we do something like this: equal parent of I minus 1. And similarly, if all the parents are same, then you can just remove you can just return parent of 0, since all of them are the same. Okay, so you see the parent of 6 is 8, right? So when I at this point, I know what the deepest leaves are, right? So I come inside the for loop and I see what the parents are. For these two, the parents, the map tells me the parents, right? The parents are 2, but then for this one it's 8. So this condition is not going to be met over here. Why? Because 2 and 8 are different parents. So I'm not going to continue. What I'm going to do is I'm going to mark all parents same as false. And if all parents same are false, I'm not going to return the parent. What I'm going to do is something which is very clever. I'm going to assign to the leaves the current parents. So now, देखो, this is very important. Now these becomes my leaf. You see, I'm going to do the processing, the same processing which I did for these nodes. For these 3 nodes, the same processing I'm going to do for 208. Makes sense? So the parent of 2 is 5, the parent of 0 is 1, and the parent of 8 is also 1. Again, the parents are not equal to each other. So I'm not going to return the parent. What I'm going to do is I'm going to say that, okay, make these the leaves. Now I'm going to do the processing for these two ones. The parent of 5 is 3, the parent of 1 is also 3. At this point, I'm going to return the parent because all parents are same right now. Alright, all parents are same right now. So this is how we basically solve this question. If you think about this, this is a O of n solution, but then we are taking a lot of extra space. We are taking space for for the child to parent mapping. We are taking extra space for in order to keep track of the level of each node. And then if we talk about the time complexity, then if you think about it, at maximum each node is being visited just 2 times. First, when we are keeping track of its parent, and then of its level, and then the second time over here inside of this loop, right? So I hope the solution was clear to you, and in the next video, inshallah, we are going to cover what the recursive approach of this problem is going to be, right?